All right, today we're going to talk about more R programming basics. Any burning questions from last time that you can think of immediately? Okay. So last time we started with a data set that's already made, and then we kind of played around with inspecting it. Today we're going to learn about how you make things from scratch in R. And then we're gonna make up our own data set, and then we're going to do a really simple regression on it so that you can finally trust that R will do what you think it does. I didn't really trust R until I sort of made something that I knew what would happen, and then it actually did it, so I felt good about it. So to summarize, first we're going to talk about functions and arguments today. We've been using functions, but we're going to learn what the parts are actually called and how to use them in different ways. We're also going to learn about making vectors and data frames. So a vector is what R calls values that appear in the bottom right. So we'll learn how to create those in different ways. And let's say you have a bunch of variables. How do you put them together into a data set? We'll learn that too. And then we're going to talk about a topic which will take a lot more time in the future, but we're just going to get a brief intro to it, which is all the different ways you can use square brackets. So we've been using square brackets on the right. Today we're going to use them on the left and talk about what the difference is. You can use this for recoding and classifying your data. As you'll see in the future, square brackets are really the workhorse of data management, and the different ways that you put them together is going to help you accomplish, or they accomplish different tasks that you might want to do in R. And for our activity, we're going to make up a fake data set using these steps, and then we're going to try running a simple regression on it. So this isn't immediately obvious, but the reason why making a data set is important is because everything in R counts as data, remember. So even the functions themselves are sort of like a data type. And often, if you can make a very simple object, a data object, you can do really complicated stuff. So for example, I might want to make an object that has all the new names that I want my data set, and I can assign it to what the existing names were. And you'll see in this example of recoding and classifying why it might be important to be able to build tiny temporary data sets like this to get your work done. So the first thing I want to talk about is I want to formalize what you already know about functions. And I showed you a little bit of this by accident last time because it came up in questions. But we've been mostly using functions that have one argument. So this would be things like sine and cosine in a calculator. If you use mean or summary, you can put in a variable and it will apply it to that object. So like you're really, even if you say the mean of x could be multiple values, but you're really only putting one thing into the function, and that is like the variable x. But functions can actually have multiple things fed into them. And you have to have a system for helping R keep track of what is what. So here's an example of a function. R norm pulls numbers from a random normal distribution. And you can imagine there's different parameters of a normal distribution. So you have to have a way to tell R what those are. And the way you do it is just by using equal sign and commas. So we're going to learn about commas with using brackets. Remember, the comma with the square brackets is how you specify the difference between the two indices or more indices. And we already used equal sign. Remember, equal is like an assignment. It does the same thing as the arrow. So the way I think about this is I'm kind of temporarily telling R the value of a couple of variables inside of this function. So for this R normal function, I'm going to set n equals 1,000, mean equals 10, and standard deviation equals 2. So this is how you'll do every function from now on. And I'll talk about why you were able to do this without specifying any of this option equals syntax. So just to review, the arguments are the things separated by commas. I guess the values of the arguments here are 1,000, 10, and 2, and the names of the arguments are n, mean, and sd. So feel free to try this in R. It should work without anything else at this point. So to sort of illustrate how this works, I'm going to talk about 3 examples of simple functions that take multiple arguments. And this is going to apply directly to our example today. We're going to learn how to create really simple vectors. These are like variables that float outside of any data set. So the 3 simplest ways to do this are the concatenate function, C, the repeat function rep, and the sequence function seq. And I chose these because they're useful, but also because it illustrates the difference in how functions can work. So on the top, what C does is it'll combine all of these arguments together into one vector or one value. So if I then assign this first line to something else using an arrow equal sign, I could like save a variable. You'll notice that none of the arguments here are named. There's no equal signs. And that's because you don't always have to name the arguments. If you don't name them, R just feeds them in and matches them the best it can. So in this case, all the arguments of C are the same. They're just things to put in the vector. So R doesn't really need you to label them. So here it says, okay, well, I'll connect them in the order that the user puts them in. So really the order here is important. For the repeat function, you can actually, it takes two arguments. It takes the thing to repeat and the number of times to repeat it. So this will create a sequence of 9, so that's 100 long. And you'll notice here I've named the second argument but not the first argument. So R is able to say, okay, well the first thing in the repeat argument is going to be the thing that I'm repeating, and the second thing, okay, well the user's named this, so I know that's the times. And we'll see how to figure out when things need names or not in a minute. But this is an example of how you can mix and match sort of using and not using the names of arguments. The third example is sequence. This will create a step sequence. So if I want to get all the numbers from 1 to 1,000 and step by 5, so this will be 1, I think 6, 9, etc. Keep adding 5. You can use the sequence function. And in this function, I have named all the arguments. You usually want to put as many names as you can so that it's clear what you're doing to other people. And I'll show you some examples of how you can mix and match even with Seq later, but this is sort of the basic way you would put stuff in. Another example of the way that R uses arguments is the data frame function. So remember, data frames are what R calls data sets. And here, the names of the arguments you put in, rather than being something that's already set, like in the normal distribution example. So for every R norm, you're always going to have to specify the mean and the standard deviation, right? Those are like the consistent names of those arguments. With data frame, R actually takes the names of your arguments and makes those the names in your data frame. So last time or the time before last, I said that a data frame is basically just a matrix with labels on it, or names on it. So here it takes the argument names and substitutes them for the names of the variables in your data frame. So here X, Y, and Z that's the actual data. So X is like if maybe I created X using R norm and an assignment arrow. X is just a vector, Y is a vector, and Z is a vector. And A, B, and C are what I want to call the three variables in my data frame. So if you want to run this code, you need to, and I'll run this in a minute, but you need to create X, Y, and Z somehow. And they need to be the same length. Since your data set needs to have, each variable needs to be the same length in your data set. If you want them to be different lengths because of missing values, you have to put in missing values yourself. Any questions so far? We'll get a chance to try this out in a minute. Hopefully you'll see what's going on.
Do the spaces matter?
That's a good question. So the spaces, they really don't matter. You can. I like to have lots of extra space, but this would be fine if there was no spaces between them. Okay. The only time spaces ever matter in R is if they're inside of a quote block. So if I have, an example. Let's say I have some code for the participant number. If I had A2, and then I had A space 2. This is the only time that it's really space sensitive. So, I encourage you to put as much white space as you can because it makes it easier to read your code. But at the end of the day, you're going to have a preference. Yeah?
You need quotations around X, Y, and Z to get it to work.
Oh, yeah. So that would be if you want if X, Y, and Z aren't defined, you could actually put in the value. So if you did, here, let me actually just show you what that does. Because I think I can replicate. So if I say data frame A equals X, B equals Y, C equals Z, Okay, well, I don't really care about the warning message, but here's my data set that it made. So x has one. A is a variable that just has the value x. B just has the value y, and C has the value z. So let me save this so I can show you in the data view. So if I call this dat and run it, it'll now create the dat variable. So this is using quotes. So if I look at this, R basically will fill in x, y, and z as the values. But I could do something like this too. If I said x is 1 to 10, y is 10 to 1, and z is repeat 5 times equals 10. So here, if I actually make x, y, and z, I can. This will actually work without it because, like, what's happening is R can now look up the values x, y, and z. Because if you don't make them first, it won't be able to find it. So if I run this, now if I look at dat, can't open this in another window. I'm sorry, but you can see that x. Now I have three variables a, b, and c that have those values. Another way you could do this is if you said, remember you can substitute stuff in anywhere you want. So if I said x equals 1 to 10, y equals 10 to, actually I want to do a, to make it the same. If I did a equals 10 to 1, a equals 1 to 10, b equals 10 to 1, and c equals rep 5 times equals 10, this should also work. And this gives me the same type of data set. So that's why it wasn't working, is because it tried to look up x, and it's like, oh, there is no x. And if you use quotes, it'll say, oh, the user wants to put in the value of x, and that's fine, too. So you can have numeric or character variables. But that's a good question, or a good comment. Sheldon?
I think also in the function, we'll go back to the first slide that had the 3 examples.
Oops, hold on. Control Shift. Yeah. This one?
Yeah. So for the second wrap and the sequence, and you don't have to name the argument names, right?
Yeah. So if you don't name an argument, R will put it in the first available slot. So here, the first argument of rep. Here, I'll show you how to look up what the argument order is. If you run question mark and then the name of a function, so I do question mark rep. This is sort of like an operator for rep. If I run this, you'll get the help page that pops up, and here it shows you the order of the arguments. I'll explain what this means, but in this case, it's basically referring to this function. And we'll talk about how to do this later, or how to tell this in the functions lecture. But x is going to be the first argument, and times the second argument. So what's actually happening with rep is it sees my first unlabeled argument, or unnamed argument 5, and so it matches that to the first argument in rep. And then it takes, okay, well, times obviously goes with times because I named it. And you can look down here and see what x is, and it says x is a vector or a factor of stuff I don't understand, right? So the R help can be confusing to understand, but and there's ways to look at this so that it makes sense. But basically x is the thing that you're repeating. It might say that in details actually. Let's see. Yeah, so it's kind of a mess here, but the simple functions are so close to the C code that there's not really much to explain. But I'll show you with the gln function today. Some of these have better help than others. Yeah.
Does the order matter if you specify all the arguments?
The order, so that it doesn't. So that overrides R's function. So if I did times equals 10 and then 5, I think this will still work. Actually, just run this part and see if we get the same thing. So basically what's happening here is R says, okay, times equals 10. So it always starts on the left. It says times equals 10. I'm going to assign that. Then I come to my first unnamed argument, and I match that to my first unspecified argument. So basically it fills it into X because that's the first thing it doesn't know about.
So that's the importance of naming the argument. So if you just say rep 10.5,
Right.
then it will give a different answer.
Yeah, so both of these will work, but if I'm reading someone else's code, I don't know which one it does. I have to sit there and figure it out. And if I'm looking at my own code and there's a bug, it might not occur to me that this is what's happening. So rep 10.5 is different than rep 5.10. So yeah, you always want to name the arguments as much as you can.
And the argument always has to go on the left.
Yeah, it's always argument equals something. Yeah. Good question. So that's sort of a little intro to functions. We'll have another whole lecture on functions later, but the other thing I want to talk about is using brackets in different ways. So we've kind of focused on one way, and I might have shown you another way last time, but we've been mostly using brackets for reducing objects. So I start with an object, and then I specify some sort of subset here using a logical expression. And then I can assign that to an object, or I can just run it. And I'm going to call this like right side brackets. And what this does is it basically makes a copy of the subset. If you just run it, it'll spit it out to the console. If you can save it to an object like X. So, just showing our little example here. If we remember what dat is, it's this little data set with A, B, and C. I can reduce, I need 2 indexes because it's a 2-dimensional object. I can reduce the size of dat by specifying something about its rows and columns. So just in this example, I can say, okay, I want rows 1 through 5, and I want columns where C, so dat $C equals, oh, well, that's all the same. So let's say columns where B is greater than 5. Oh wait, that doesn't make any sense. I want to specify the rows based on the values. So I'll take the observations where the value of B is greater than 5, and I'll take columns. Let's say column 1. If I run that, I will get something that's confusing, right? So what I should get, so if I say, okay, I'm going to take B greater than 5, which is going to be this half of the data set, right? And then I'm going to take just column 1, but then I get 1, 2, 3, 4, 5. What's happening is it is pulling out column 1, but it's because this is now a one-dimensional object, it's just displaying it in this order. So it did actually do what I wanted. Just to show you, if I change this to 1 and 2, that's going to preserve the dimensions of the object because it's 2-dimensional. It'll save the orientation. If I really want to make it the right orientation, I can force R to do it using T, which I'll talk about in data management. But T is basically transpose. Always add more if it doesn't do what you want. Okay. Okay. So I keep telling it. So the first transpose doesn't do anything because I'm starting with a vector and I'm telling it to transpose. And so it says I don't know how to do that. I'll talk about this later, but it says I don't know how to do that, so I'm going to just turn it into a matrix first. So it does that. And then it says, okay, now I'm going to transpose this, so it actually gives you this. And I'll talk about why this works in data management. Sorry to sort of preview all these things, but just to sort of show you that it does give you what you're expecting eventually. So, sorry, go ahead.
Once you've specified the data frame or the object that you're going to subset from, is it then necessary to have to say this is the data frame where this variable?
Yeah, each time. Yeah, so I typically do, but there's ways to get around it. I'll just show you 2 of them. One, which I don't recommend, but is fine for many cases, is using attach. So what attach does is it's kind of like manually running a data step in SAS. It like puts you into that data set, and every reference you make is within that data set. So if I attach to dat here, now I don't see any output, but I'm technically inside of dat. So now if I look at A, it basically looks up A within this. It's called an environment. So it looks up an A within the dat environment, which I'm attached to. I can still reference global stuff. So if I run X, it still knows, which acts as what I use to make A, so it's the same. But I can still look at global stuff. And then when you're done with that data set, you can use detach dat. The reason why this isn't preferred is because it creates like another program state that's not immediately obvious. So generally, you can tell the state of your program by just like looking to see what your data is. It's like what data is defined, right? But if there's no easy way to tell what I'm attached to. I think there's a way to inspect it somehow, but if I'm getting an error, I'm like, oh, why is this not working? And maybe, oh, I actually attached to this data set, and there's a global version and a local version. Which one am I using? So I typically avoid that. Another way is there's some functions that actually you can specify an environment in. So you can say, I want to work within the DAT data set, and I'll show you an example today with the GLN, but I think if you use subset, you can also specify the data set here. Yeah, I think there's a way to do it this way, but basically there's some functions where you have like, some generic thing, and you basically put in data equals dat. And that'll say, for the purposes of this function, pretend like you're attached to dat. Does that make sense? My solution is to typically have really short data set names because I'm lazy, so I'll basically call everything dat will be my final analysis data set. Or burst is pretty short, you can call it B or something. But yeah, sometimes it's worth it to type it out to make it like clearer to yourself, even though I strongly resist it. So I think this is pretty much the last slide, and then we'll experiment a little bit more. But the point is, if on the right you can reduce stuff, if you put the brackets on the left, you can actually replace some subset of an object. So here I'm telling R to look up the subset of this object, and then I can override it with anything else. So this is backwards from what we've been doing. So the new rub of this is that the length must be the same size. So if I'm going to say, okay, we'll replace variable A, right, what I'm replacing with has to be the right length, so 10. So if I want to say, let me just let me find the expression I had before. So it was this area here. I have too many parentheses, but we'll discover that shortly. Okay, so I've got an expression here that refers to part of my DAT data set. So remember, it's basically the first column, the first 5 observations, right? So this is just printing out what's there. So now I can write anything to replace that with. So let's say I want to replace this with 100, 67, 3, 2, 1. So notice that this is the right length. It's 5 long. So if I run this, R will tell me nothing, which means it's okay. And then I can look at DAT over here and see that it's overwritten parts of my data set. So this is all going to be in the data management thing later, but just to get your mind around the idea that you can replace, you can use expressions to specify places to replace stuff, if that makes sense. And we'll have some practice with this. So the two cases that it's easiest for me to think about are, well, let me do this slide first, sorry, is replacing the names of an object. So if I make a vector that's the same length as the number of columns of a data frame, I can rewrite these new names to the names part of the data set. So remember, all you have to do is write an expression that returns what you want to replace. So here I write names data set, that spits out the names. Well, if I overwrite that location, it actually overwrites the names of that object. And this is like persistent because it's actually affecting the object itself. And if I want to make my expression specific to the second name of the data set, I can also overwrite just that. As long as the length matches as long as the length on the right matches the length on the left, you're fine. You can do whatever you want. So then why does this actually work? So it's because R treats everything on the left side of the assignment as a reference to something. So it treats it as a reference on the right, but you're kind of doing something with it, and on the left you're doing something to it. Whenever you are making a new vector or value or data set, some new thing, what R is doing is it says, okay, well I can't find the reference on the left, so I'm going to make it and then assign it as value. If you have something on the right that R doesn't know about, it's going to panic because it's not obvious what to do. So here's two examples of saying, okay, well, if this is the right length, it works. This wouldn't work, aside from me missing the parentheses. This doesn't work because the length is wrong. So the right side is length 2, and the left side is length 1. So I'm saying take a vector, take the fourth slot, and put in 2 values. It doesn't know what to do. And some things you can't replace. The other day I replaced what plus does. I also can't replace 2. So this is me writing 3 to 2, and R says, no, I can't do that. I won't let you reassign what 2 is. I think you actually can overwrite 2 somehow, but actually what's happening is it says 1 plus 1 is kind of like this temporary result, and it doesn't know how to assign that a value because it doesn't really, it's not a basic thing.
How does that interact with the, this has nothing to do with the true, false?
Mm-hmm.
Okay.
Yeah, you could put, here, assuming vector is like 3 long, I could put vector true, comma, false. And that would say replace the first 2 elements. So you can always either use, you can either use true falses, you can use a Boolean argument, which is basically just producing true falses, or you can use the index. And sometimes you can use the name of things. So like the name of the column or the variable name. So another example of overwriting things is classifying variables. So this is a really basic data management thing. So let's say I've got an example variable that's numeric. So here it just goes from 1 to 100. How do I classify this into different categories? Let's say I want to make this into high, medium, and low. Well, the manual way to do this is a 2-step process. First, create an empty vector that's the right length. So here I'm using rep to fill in missing a number of times equal to the length of the old variable. So remember, the length has to match. So this is a way to make basically a blank template that's the right length. So I'm looking at the length of the example. And here I didn't specify times, but because R knows this is the second argument and times is the second named argument, it just fills it in.
This example is something already created earlier.
Yes, yeah, so I create, sorry, this should be AX. So this should be length of EX, which is just that EX. So then once you've made the place to put the data, then you can fill it in. So again, I'm going to reference new on the left because this is what I'm actually overriding as my new template. So I'm going to say new in the positions where the value of X is less than 30, I'm going to write low to those slots. You can also write a complex Boolean statement. So here I'm saying, okay, take new, look up the positions where EX is greater than or equal to 30 and EX is less than 75. So again, this is just producing true-false values, this inner statement that then feeds into the indexing system. I'm going to assign these values to medium, and then I'm going to assign, this should be lowercase new. I'm going to assign the remaining values, or here I'm manually specifying greater than or equal to 75 to high. So this is the really manual way that you could classify a variable. There's other functions to do this that you'll learn, but it's good to understand what it's doing and how to fall back on this if you need to. So I'll leave this up if you want to try it, but so again, the errors are this should be EX and that should be lowercase new. Any questions before I kind of run through the example stuff, which contains this kind of idea too? So the purpose of today's exercise is to practice using a really simple regression on a data set that we built ourselves to prove to ourselves that R actually works. And to do this, we're going to learn a new operator. So we've already learned about plus, minus, times. R has a model operator, which I interpret as predicted by, and it's the squiggle. I forget what this is called. It's not tilde. Is this tilde? Okay. So this is the predicted by operator. And the way that you write models in R is just like you would write models for any other class, or for real life, except instead of equals, you put in the tilde. So, if I've got, let's say I've got a linear model where y equals mx plus b. It's very similar to the SAS format where you can ignore, you don't have to put in the intercept, but there's a way to do it if you want. And then for each model element, you don't have to put in the coefficient because R figures that out, but you put in the term. So a more concrete example would be, let's say outcome, so out equals exposure times beta 1, plus covariate times beta 2, plus plus some intercept, beta 0, which we usually ignore, and then plus the residual, which we don't usually think about either. So if this is my basic equation, the way I put it into R is I just put in the name of the outcome on the right, so out, the left. You put out on the left. And then you're going to put in just the names of the variables that go along with each coefficient. So here I would say exp plus covariate. So this is how you replicate specifying this model in R. So I'll just share a brief example of that using made up data. So if you want to do it on your own instead, feel free to look up the slides too if you need the steps. But we're going to basically make a data set with fake random variables that we control. We're going to make a fake outcome based on an equation that we specify. So we can manually set this to be true, and we know what the parameters are. Like we can set b1 equals 2 and b2 equals 1 or something like that. So we're gonna manually fake this data so that y matches the regression equation. We're going to practice making a binary variable from a categorical variable by splitting it on the mean. And then we're going to use the gln function to build a model. So here, this would be an example of x is the exposure and z is the covariate from this formula. I just put y is predicted by x plus z. This is just a linear regression. And then if you want to run a logistic regression, you can put in the binary version of y that we made and specify the family argument. So this looks complicated, but you'll see that it's not very much code. And hopefully by playing around with it, you can see what's going on. And hopefully we should have enough time. So I'm just going to make a new script and make it big so you can see everything I've done. So fake regression. All right, so I'm going to start with the independent variable. I'm going to call it x. And you can call it something else if you want to make this more fun. You can call it blood pressure or something, but you're gonna end up with nonsensical blood pressure values unless you really play around with it. Let's just do that. Let's just do blood pressure. Okay, blood pressure is going to be R norm. So remember, this is a function that pulls from a random distribution. I'm going to set in, which is a sample size. I'm going to put that to 1,000 just so it doesn't take too long. I'm going to set the mean to 120 because I guess that's sort of, hopefully this gives something sensical. And then, so this is systolic blood pressure. And then I'm going to set the standard deviation to, let's just do 10. We'll probably have a couple people who are dead, but should be fine. Okay, so I'm going to make blood pressure. All right, great. I'm going to make a covariate called age. And you can use spaces to try and line your code up so it looks nicer. So I'll put a space up there. R norm. So we're going to call this n equals 1,000 because we want it to match. Let's make the mean 50. And the standard deviation is going to be we don't want negative values, so I'm going to be pretty conservative and say 5. Hopefully that should keep us pretty, I mean, it doesn't really matter because it's fake, but, right, so you're free to line up your things if you want. I like to line up the arguments like this in the final, yeah.
Can you give it an argument X?
Not, well, yeah, you can either trim it if you want. Actually, that's a good example. Let's show how you do that. So I would make BP, well, there's other functions that would do this for you, but just manually you can do, so let's look at BP here. So I just ran those two things. Looks good. It's basically a bunch of random numbers. And I can kind of look at the summary of BP to get the maximum value. Okay, so the max is 156. Let's just pretend we want to trim it at 150. So all I would do is then have a line down here that says, remember I can use brackets on the left, so BP where BP is greater than 50, 150 is 150. Now I could also redraw until I got everything below 150, and that's what I would do if I was doing it. But I won't show the full code for that, but I can show you that if interested. But my master's paper was a Bayesian spatial resampling process, and I basically just, you can make an equivalent distribution by redrawing it until it matches what you want, as long as it's uniform. Yeah. Here I'm saying, sorry, it's too crowded for these whiteboards, but yeah. So here I'm actually just saying, okay, take everyone that's here and pile them up here. So my distribution now is like this, right? If I was using a resampling approach, I would make a loop, and I would say, basically resample these across the entire spectrum until nothing is left here, and then like end the loop. Somebody's probably written a more elegant function you can find in the package, and maybe that's a good example for something that would be useful in the packages today. But again, there's like a million ways you can think about it. So here I'm just truncating it, and if I take the histogram of BP, I should see that it looks. Well, here there's not that many people, but they're put in there. If I want to be more radical, I can say BP where BP is greater than 120. So here I'm trimming it on the right at a really ridiculous level. So here it's piled everyone on this half of the distribution is on here. So I think there's a name for what this is, like half. I don't remember what it is though, but it's kind of like half of a. Well, no, I guess it would be like a mirrored. Like basically, I would resample everyone until everyone was less than something. I think that's some sort of distribution, but I forget what it's called. Anyways, this is one of the great things I like about R is you can really make whatever distributions you want pretty easily. You just have to think about how it works, and sometimes you can find examples of code that does it, but it's super flexible about getting distributions you want.
So once you run that, is our BP value now permanently changed?
Yeah, right. Yeah, exactly.
It's like,
yeah. So
okay.
Whenever you have the brackets on the left and you run it, you're like permanently changing this BP. I mean, we're still free to change it, and we can actually redraw it. But yeah, that BP is actually changed. Yeah.
What BP do you want to change it?
Yeah, I would say what I would do is I'd make a copy. I'd say BP1 is BP. And then I would make this one say BP1 where BP is greater than 120. So this will just edit the copy. So I'll just kind of do it manually. All right, so it doesn't really matter what my distribution is for this purpose. So I'm just going to keep BP the way it is now. You can use whatever BP you want. It still should work. So so I've made age. Let me just make sure that exists. All right, so now I've got an X and a covariate. So I'm going to just write a math expression to manually build my outcome value based on these two things. So actually, let's put this in a data set so you can sort of see a realistic example. So we've got the exposure and we've got the covariate. So let's put them together with data frame. So if I do data frame BP comma age, if I just run this, it's going to spit out the data frame over here. Right? Let me go to the top here. But that's not what I want. I actually want to make it called something. So I'll call this epi, because it's our epi data set. Whoops. Not there. Okay, epi data frame BPH. Okay, so I've got epi now. So now I can write an equation for what I want my outcome to be. So this is going to be super unrealistic because it's like a linear thing, but you can imagine extrapolating this to like risk ratios or something. But let's say that my outcome variable is going to be called, what would be continuous? Let's just say we have a marker of something in the blood. Let's say we've got like a, what's the stress? No, there's something in the blood that like is a marker of stress. It doesn't really matter, but I'll just. Oh yeah, C-reactive protein. Okay, yeah. I was trying to tell my doctor what this was the other day, and I couldn't remember, and they didn't know, and I was like, oh, that's weird, but yeah, okay, but we know what it is. Okay, so C-reactive protein is going to be let's say it's very related to your age. Sorry, your blood pressure. So it's going to be blood pressure times 100. Again, the scale doesn't make any sense here, but you know, let's say the true coefficient is 100, right? Plus age times 5. So age is not as important maybe, but you know the scale is different, so who knows? And then the last thing I need to do is I need to make an error term, right? So if I just have CRP equals blood pressure plus age, I'm going to have a perfect regression. R is going to freak out because, you know, how do I estimate, you know, my standard, what is it, deviance or whatever based on a perfect model? So I'm going to put in some error. So let's have a pretty small error term by just saying R norm. So n equals 1,000 times equal, whoops, wrong function. Mean equals, let's just use standard errors. Unrealistic, but let's meet all of our model assumptions and see what happens here. Okay, okay. So mean 0, standard deviation 1. All right. So here I'm overriding CRP. Oh, but wait, CRP doesn't exist. So I'm making a new variable called CRP, and I'm writing in the value of this equation. So remember, these are all vectors. So what it's going to do is, like, for each position in CRP, it's going to like fill in the appropriate value of age and BP. This would be kind of like if I did a loop and I said for I, like in SAS, you know, you did a loop for 1,000 and say for each thing, or in SAS you could do this in the data step, but this is doing the same thing. It's basically doing vector math, but you can just think of it as doing it one at a time for the whole thing. Yeah, Sheldon. Oh, yeah, that's a great. So CRP is not in my data set, right? But I want it to go in my data set too. So I can actually just tell it that the CRP should be in the data set. So if I say epi $CRP, now remember my reference is pointing to something. And R knows that if I point to a non-existing vector within a data set or like a variable, it's going to make that. So if I run this now, I don't see anything, but if I look at my names of epi, I can see that it's there, and I can look at the head, which returns the top of a data set, and it looks good, right? These are all really, I don't know what scale this is, but it seems fine for now. You know, we have some numbers. All right, so now we've got a fake data set that has a true model, and let's see how close we get there with only 1,000 observations. So I'm going to use GLM, which we'll cover later, but this is an introduction, which is you know, generalized linear model. And we're just going to use the linear version, which is super easy to type in. So I'm going to say GLM, my response is CRP, predicted by BP plus age. And I want to do it within the data set. So this is a question earlier. What if I want to not type it out? Well, I can say data equals epi. So it'll look into epi and do this. You can also just write epi $CRP squiggle epi $BP plus epi $age. You can mix and match them, but data equals epi just kind of attaches to this data set for the purposes of this function. So by default, this is a linear regression, so I'll just run it like this and see what we get. So not too much, unfortunately, but remember that R just prints the default output if you don't tell it what to do. So if I just run GLM, I kind of get some coefficients, which look pretty good, but I don't get any other statistics. Like I I don't get the errors, or I guess it gives me degrees of freedom, which I could find other ways, but it doesn't give me much. This is a good illustration of why object orientation is important. So in SAS, when you run a model, you kind of get all your output at once. And you can give it options to say, what do I want, what do I not want? In R, the approach is instead, we're going to make a new object called a model object. This model object is going to contain all the information about the model fit, just like our data set contains all the information about our data. And we're going to use functions on our model object to get out different results. So you don't have to, it's really easy to do. It sounds, I'm just going to call this M1 for model 1, and you just assign it to M1. R will automatically make this into a model object because it just matches. Like before, you could put anything on the right and name it, and R will just respect the type. So if I run that, here is my M1, a large JLM with 30 elements, and there's a little bit more information. But the short answer for now is you can easily access the sort of SAS comparable output by using summary. So remember, if you use summary on a variable, it gives you the 5-stat summary of the variable. If you use summary on a data set, it gives you the 5-stat on all the variables. If you use summary on a model object, it gives you the basic summary of the model object. So if I take the summary of M1, now I've got the actual output of my model that I would want to see. So I can see, here's, this table is bad because my console was really normal, but really narrow. But you can see, okay, well there's the estimate, there's the standard error, there's the t-value, and there's the p-value, which don't look at this. This is heresy, but this is basically the stuff you would want to get out. But wait, there's more. So if I look at what other functions might I use to look at M1? So summary works. What if I look at the names of M1? Remember how I said that a data frame is a matrix with names on the parts? Well, guess what? The parts of a model object also have names, and you can use those to access it just like you use the variable names to access the data set. So let's say I want to make a plot of the residuals versus the value of y, right? I forget what it's called, but this is some sort of diagnostic tool, right? Okay, so the residuals is just M1 $ residuals. Okay, so first I say, okay, this is the reference. Let me see if it does anything. So I run this. All right, this could be residuals. And then I've got y1. Let's try plotting the two against each other. So we haven't covered this, but plot can take multiple arguments. I'm going to plot y. Sorry, not y. This is going to be what was that? A CRP. But yeah, I mean, you could also do it based on other covariates too. But so here I'm going to plot the x. So the plot with two arguments is x comma y. So I'm going to plot CRP as the x value and the residuals as the y value. So if I run this, I get a scatter plot. Again, I don't remember what it's called because it's been forever since I took biostats, but I can see, okay, well, does this match the distribution of residuals I'm assuming in my model? I would say without knowing much more, this is probably a pretty good model because I literally made it into a linear relationship with a small error term. So this is probably pretty good distribution. We only have a few minutes, so I'll just show you how easy it is to do a logistic regression. First, we need to make a binary outcome, so I'm going to classify CRP into 1 and 0. So I'll just call this CRPB is going to be rep in A. So remember, you're going to fill in missing to start with, and then the length of epi $BP. Okay. So I'm going to make, okay, it looks like the right length. Now I'm going to say CRPB where epi $BP is greater than mean of epi $BP is going to be 1. So this is, I've combined a lot of things here, but all I'm doing is I'm saying, okay, take the value of epi BP, see if it's greater than its own mean, and if it is, write the value of our new vector 1. And then I can be really lazy and say CRPB, and I can say after if anyone has a question about this, but I'm going to take CRBP and put in the remaining values, which are all missing. I'm going to call that 0. So don't usually do this, but this is just a lazy way to do it. So CRBP where CRBP is missing is.ina. So take CRBP, look up where it's missing, and then assign it 0. Oh. CRP. Okay, so what did I do wrong? Oh, this needs to be BP. Thank you. Okay, so again, I can't type, but okay. So I've really crudely made this dichotomous. If I want to make a well, I'll figure out a way to summarize this after the class. But basically, you just use GLM. Oh, let's actually put this into our data set. So I'm going to say epi $CRBP is going to be CRBP. So this line just puts it in, right? Though I don't really have to do this. Then I'm going to copy my model object down here, M2, and CRBP. What did I call it? CRBP? Oh, that's why I'm confused. I was confusing with blood pressure. Okay, well I'm just gonna type what it is, but just it's CRPB, not this. Okay. So all you do to make it logistic is you just add another argument. It's all the same thing going on under the hood. So I'm gonna say family, which is like the link function. Sorry, this isn't the link function. This is the family. Then you're gonna say binomial, which is the outcome family, and then you're going to say binomial of logit. And I'll talk about why this actually works later, but basically what's happening is you're creating another object called a family object, which is the logistic regression, like family. Oh, thank you. So this function, if I just run it to show you what this is actually doing, this is an object called the binomial family with logit length. This is just our logistic regression. So if I feed that object into the family argument, I can get M2, and it doesn't converge because I probably had such high things, but let's see if we can just get it to work on age, maybe. Oh, it's because I referenced it based on BP. I should have done it based on, hold on a minute. That's why. I didn't dichotomize it correctly. Okay, so the length should be okay, but now I'm going to basically rebuild this based on its own value instead of it. So I basically had cross-referenced it by another variable and then put that variable in the model, and then of course it's not going to be, you know, it's like everything was either 1 or 0 based on the thing I put in the model. Okay, so it's too good. So now let's actually try this without ridiculous things. So again, all I did was I fixed this so that this references itself rather than the other value. Now if I look at summary of CRBP, whoops, nope, summary of N2. All right, now I've got the logistic regression output. We'll have more on this, but basically this is going to give me the stuff on the log scale. And I need to transform it back if I want to get like the odds ratios. And to do that, I would just say exp of M2. I think this works. Whoops, let's try coef. Okay, so here's how I would get my actual, so I'm saying exponentiate, and then the coef function pulls out the coefficients from the model. Again, we'll talk about this later, but I just wanted to show you this pretty simple. And then I would, if I want to get the confidence interval on the log scale, instead of coef, I put confint. Is that right? Maybe confint? Yeah, okay. So then I can get the profile likelihood here. So, you know, age, my mean estimate is not very big, and my confidence interval includes the null here. And that's because, you know, we didn't really make it have a very strong effect compared to the overwhelming effect of BP here, I would say. Also, age doesn't really have all that much variation potentially, but let me just see if this works. Okay, you can plot the model object and we'll get something. You know, sometimes I'll just see what happens here. Okay, so, actually this gives me interactive plot. So if I just plot the model object, it'll give me these same graphs in sequence. So I can get the residuals versus fitted, I can get normal QQ plot. Mike might have showed you this the other day, but you know, the idea is just try stuff and see when it works. Sorry to keep you over. I mean, you're free to go, but if you have a question, feel free to stick around and ask. Again, this is just an illustration. Don't worry about the model stuff, but just to show you that this is why it might be useful to be able to build stuff yourself.